Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of game theory with engineering applications. We'll dive into key concepts like what is a game, game design schema, game design fundamentals, engineering application of game theory. Let's get started. Slide 1. What is a game? Hello everyone. Today, we are diving into game theory and its engineering applications. First, let's start by understanding what a game is in this context. A game is any situation where multiple participants, called players, make strategic decisions, aiming to maximize their own benefits while considering the decisions of others. Players, individuals or entities making decisions in the game. Strategies, the set of choices a player can make. Payoffs, the outcomes that players receive based on their strategies. Rules, the predefined structure dictating how the game operates. Example, consider two companies deciding whether to lower their product prices. Their profits depend not only on their choice but also on what the competitor does. This is a game in action. Significance, game theory helps analyze decision-making in competitive environments, ensuring optimal strategies in economics, engineering, and even artificial intelligence. Slide 2. Game Design Schema. Now that we understand what a game is, let's explore how we design a game using the game design schema. This schema helps in structuring a game systematically. 1. Objective. What is the purpose of the game? E.g., maximizing profits, defeating an opponent, survival in a competitive system. 2. Players and roles. Who are the decision makers? Are they independent or do they form coalitions? 3. Rules and constraints. What can the players do? Any restrictions in their actions? 4. Strategies and choices. What different strategies are available? 5. Payoff system. How are rewards and consequences assigned to different strategies? 6. Equilibrium and stability. When does the game reach stability where no player wants to change their strategy? 7. Uncertainty and information. Do players have complete information or only partial knowledge? Example, in chess, the objective is to checkmate the opponent. The players are two individuals, the rules define valid moves, and the strategies include offensive and defensive gameplay. Significance. A well-structured schema ensures balanced and engaging game dynamics, improving decision-making in real-world scenarios. Slide 3. Fundamentals of game design. A good game is built on strong fundamentals. Let's discuss the core elements of game design. 1. Balance, ensuring fairness so no player has an unfair advantage. 2. Interactivity, players should have meaningful choices that influence the game. 3. Feedback system, players should know the impact of their actions, e.g., scoreboards, warnings. 4. Progression, challenges should increase as the game progresses. 5. Competition and cooperation, games can be competitive, zero-sum, or cooperative, team-based problem solving. 6. Uncertainty, adding elements of randomness or hidden information to make the game exciting. 7. Replayability, a well-designed game remains engaging over multiple sessions. Example, in a traffic simulation, game design principles help model how autonomous cars interact and optimize movement, reducing congestion. Significance, applying these fundamentals ensures games, or simulations, provide real-world value in decision-making, engineering, and system optimization. Slide 4. Engineering applications of game theory. Game theory is not just theoretical, it has vast applications in engineering. Let's explore a few important ones. 1. Network security, identifying optimal defense strategies against cyber threats, e.g., intrusion detection systems use game theory to anticipate attacks. 2. Wireless communication, allocating bandwidth efficiently between competing users. 3. Autonomous vehicles, self-driving cars use game theory to navigate traffic while minimizing risks. Point 4. Power grid management, optimizing power distribution among users. 5. AI and robotics, multi-agent systems where robots coordinate actions using game theoretic principles. Point 6. Supply chain optimization, businesses optimize pricing and inventory based on competitors' actions. 7. Auction systems, bidding strategies in spectrum auctions, online advertisements, etc. Example, in AI, game theory helps in reinforcement learning, where an AI agent learns the best actions based on competing agents' moves. Significance, engineering applications of game theory help optimize real-world problems, making systems smarter, efficient, and competitive. Slide 5. Differences between conventional and game theory approaches. In this slide, we will explore the key differences between conventional decision-making models and game theory approaches. While both frameworks aim to guide decision-making, they differ significantly in how they handle participants, decision processes, and outcomes. 1. Number of participants. Conventional models typically involve a single entity making decisions in isolation. Game theory, on the other hand, focuses on multiple entities or agents, each influencing the outcomes through their actions. Example, in supply chain logistics, conventional models optimize a company's internal operations, while game theory considers competitors' actions and market dynamics. 2. Decision dependency. In conventional decision-making, decisions are independent, the outcome depends solely on the entity's choices. In contrast, game theory considers interdependent decisions, where each player's choice affects and is affected by others. Example, pricing a product without considering competitors uses a conventional approach, while game theory would factor in competitive reactions. 3. Outcome prediction. Conventional models rely on fixed rules and assume static environments, while game theory accepts dynamic outcomes, changing as players interact and respond. Example, project scheduling uses fixed timelines, while game theory applies to dynamic competition like pricing wars. 4. Conflict and competition. Conventional approaches assume no strategic conflict, but game theory explicitly models conflict and cooperation among agents. Example, legal negotiations are modeled through game theory, while standard budgeting follows conventional approaches. 5. Risk assessment. Conventional models handle risk statically, treating probabilities as fixed. Game theory uses probabilistic outcomes, considering how agents adjust under uncertainty. Example, in cybersecurity, game theory models adaptive attackers versus defenders, while traditional models use fixed risk analysis. 6. Feedback mechanism. Conventional systems often have limited feedback, while game theory involves iterative adjustments. Players update their strategies based on others' actions. Example, automated bidding in online auctions uses real-time feedback through game theoretic models. 7. Application scope. Conventional models suit linear systems where variables interact predictably. Game theory applies to non-linear, interactive environments with multiple agents and unpredictable outcomes. Example, predicting market trends requires game theoretic analysis, while simple inventory planning uses conventional models. 8. Example, chess is a clear example of game theory. Each move depends on the opponent's actions. Traditional project scheduling, however, follows a conventional model because tasks progress independently of external competitors. 9. Significance. Understanding these differences is crucial for choosing the right framework. Game theory is effective for multi-agent, competitive environments, while conventional models suit straightforward, isolated decision-making processes. Slide 6. Common strategies in game theory. Now, let's discuss some of the most common strategies in game theory. These strategies guide decision-making in competitive and cooperative situations. 1. Nash equilibrium. This occurs when no player can improve their position by changing their strategy alone. Once players reach this point, no further unilateral changes are beneficial. Example: in online pricing, if two companies reach a price where neither can profit by undercutting the other, they have reached a Nash equilibrium. 2. Minimax strategy. This strategy involves minimizing the maximum loss. It is particularly useful in competitive environments where opponents aim to exploit weaknesses. Example: in chess, a defensive player uses minimax to avoid the worst possible outcome. 3. Dominant strategy. A dominant strategy is always the best choice, regardless of the opponent's actions. Example: in the prisoner's dilemma, confessing is a dominant strategy because it offers the safest outcome. 4. Mixed strategy. Here, players randomize their decisions to avoid predictability. It is often used when no pure dominant strategy exists. Example: in soccer, a goalie chooses random dive directions to prevent the kicker from predicting their movements. 5. Backward induction. This approach involves solving a game backward from the last move to the first. It is effective for multi-stage decision processes. Example: in chess endgames, players use backward induction to plan moves toward checkmate. 6. Tit for tat. A reciprocal strategy where players mirror the opponent's previous action. It is useful in repeated interactions. Example: in business, companies may match competitors' discounts to maintain customer loyalty. 7. Pareto efficiency. A state where no player can improve their outcome without harming another. It represents an ideal balance. Example: in resource allocation, Pareto efficiency ensures fair distribution without disadvantaging anyone. 8. Example: in network security, Nash equilibrium helps predict hacker versus defender strategies, ensuring optimal defensive measures. 9. Significance. These strategies are vital in economics, cybersecurity, and artificial intelligence, where strategic interactions define success. Slide 7. Summary: why game theory matters in engineering. This slide ties together the major insights we've discussed, highlighting the practical value of game theory across engineering applications. 1. Game theory models strategic interactions. It provides a structured framework for analyzing competitive and cooperative decisions. 2. Game design schema and fundamentals. These frameworks ensure balanced, fair, and engaging systems in game development and engineering. 3. Engineering applications. Game theory applies to real-world optimization problems like resource distribution, network security, and AI decision-making. 4. Conventional versus game theory. While conventional models work well for simple systems, game theory is essential for multi-agent environments with interdependencies. 5. Strategic thinking. Game theory promotes strategic analysis, improving decision-making across fields like AI, economics, and software engineering. 6. Real-world relevance. From autonomous vehicles to auction systems, game theory is shaping advanced technological solutions. 7. Future trends. As fields like AI and blockchain grow, game theory will play a pivotal role in managing complex and adaptive systems. 8. Example: AI-powered autonomous systems apply game theory for collaborative and competitive decision-making in real-time environments. 9. Significance. Game theory extends beyond games. It influences how modern engineering tackles multi-agent, dynamic, and strategic challenges.